Good morning, everyone. My name is Martin Roeb. I'm representing German Aerospace Center, Institute of Future Fuels, and it's a pleasure for me to be here and to talk a little bit on using concentrated sunlight for hydrogen and fuel production. I'm part of author consortium with colleagues listed here, and with this I go to the details. Uh, just mentioning, after giving a little bit background, I then go into materials for thermochemical syngas production, talk a little bit on concentrated optics, and then give some examples of solar reactors and also some demonstration cases. Yeah, this just should show you a little bit the comparison of what is needed in terms of electricity production in comparison to the total energy production. In blue, you have the electricity, and this is small, and this has been over the last 30 years, not changed very much, saying that we have less than 15% of our total energy production in terms of electricity. And what is the rest? Of course, most of the rest is fuels. And therefore, we have to look for potential solution to do also something on the fuels to make it greener than we have it at the moment. And also we need to have a look at the potentials. Here, the main message is what kind of different renewable energy sources we can use and what are their capacities. Looking at the black numbers, this is the area specific yield we are harvesting, which we can do. And if you compare biomass, geothermal, wind and hydro with solar, you see that solar has orders of magnitude higher area specific capacity, and also the total amount is much higher than the other sources of renewable energy, and therefore solar must play a role in our future portfolio of green energy supply. I concentrate on the solar energy in this graph, showing the different technology to produce fuels from renewable energy, and here it is mainly the photochemical pathway and the solar thermal pathway, which I concentrate on in the coming slide a little bit more detailed. Let's move now to materials, and here I'm giving an example for a functional material which is needed for thermochemical fuel production. And this is needed for such a process, which is a thermochemical cycle. And you can see here you have different temperatures. It's a so-called temperature swing operation, which we do with this cycle. And the central element of this cycle is a metal oxide. A metal oxide which can exist in two different oxidation states, a reduced form and an oxidized form. And the first step is an endothermal step, which is driven by concentrated solar power at temperatures much higher than 1000 degrees C. The metal oxide is reduced, oxygen is set free, and you get to the reduced form, the oxygen lean form. And this form is capable to abstract oxygen from molecules like water and CO2, which are the feedstock. And by doing so, you get synthesis gas, which is an intermediate in order to produce hydrocarbon fuels like kerosene, like diesel, like other hydrocarbon fuels. And on the other hand, you regain the oxidized form of the metal oxide, which then closes the cycle. And this is typically done on top of a solar tower, like shown here, because you need, let's say, the energy input by concentrated sunlight. Now let's have a look which kind of materials might be capable of doing so. Here some are listed, like ceria, like ferrites and perovskite, which we found out in the beginning by looking into thermodynamics, by looking into such curves which are called Ellingham diagrams, and you see the potential elements and substances which can do such kind of cycles in a thermodynamically feasible way. but you also can manipulate the properties of the materials by, for example, doping, which we did a lot, for example, by zirconia doping, which allows you to get down the maximum temperature of such a cycle, but also introducing other additional elements like ytterbium or lanthanum, which helps you with the kinetics of the process, because also those are important in order to get the cycle in a way that you have many cycles, as many cycles as possible on a day. Now let's move to the optics, in particular concentrated optics, in order to run high temperature but also low temperature processes. In concentrated optics, we differentiate between line focusing systems, for example, parabolic troughs, where you have, let's say, a tube in the focal area. It's a focal line in order to concentrate the sunlight, but the concentration is limited between 10 and maybe 200, which is the very upper end of what is possible. If you would like to get to higher concentration and higher temperature, then you typically go to parabolic dishes or to solar towers. Dishes is a little bit exotic, not very much used, so I will concentrate a little bit on the solar towers, which is made up of huge heliostat fields. You have some hundreds up to some thousands of those flat heliostats, and those are tracked according to the course of the sun and redirect the radiation onto a spot on top of the tower, where you, by overlapping the different mirror images, can up to concentration factors of, let's say, some thousand suns. Showing this in practice, here are some examples, photographs taken on the so-called Plataforma Solar de Almeria, where those facilities are being tested and being developed, a dish system, a solar tower, here a trough system, and this I didn't mention. This is a specific form of the parabolic troughs by having individual facets here and by projecting such a trough into one plane, and by allocating to each of the facets individual angle which would be tangential to such a parabolic trough. So this is a simplified form of a parabolic trough, if you like so. So this is just to show you a few examples of highly concentrating system like solar towers, like solar simulator, but I just make it short in order to give you only a few impressions on that. Here, and finally, the example of a concentrated optics. Here we are again with linear Fresnel, and this was a system built up for a PEC system. In fact, this is operated in Cologne on our campus. And here you see once more the facets which are concentrating the sunlight onto this bar here, where you can install different cells like photoelectrochemical cells, but also other devices which might run under typical conditions of slightly increased solar flux. So we have a two-axis tracking. Sunlight, as mentioned, is redirected and concentrated to some extent that you have when turning by 100 degrees C. You see, let's say, the illumination of that bar with increased solar flux. This is the size, 2.5 meters by 10 centimeters. It's done by aluminum facets. You have 20 suns which you can reach, and a reflectance of higher than 80%. So let's get now to some examples of reactors where we applied concentrated optics to certain processes. And here, starting with a process where we only needed a slight concentration of the sun, less than 20 or 10 suns. You see here example of a photocatalytic reaction on the left side, tubular receiver, one without optics, and the other one has on its back a CPC concentrator providing concentration of about 10-fold concentration for photo-oxidation. Here the example of photo-oxidizing citronellol to a fragrance to rose oxide was the example which we did in a field study, and we really could see that a certain concentration of the sunlight really helped the reaction. We were able to get much higher yields of the product by using, for example, the trough system on the right hand side, which also was tracked to the sunlight over the day. Second example is the one I already mentioned, the so-called Socrates setup, which you see on the left-hand side, a Fresnel, linear Fresnel system capable of concentrating the sunlight in order to power set up a pack device which does water decomposition, photoelectrochemical water decomposition, and in the middle you see some of the results. If you have a look at the purple and the red curve, in particular the red curve shows the hydrogen production, and it follows more or less perfectly the purple curve of the radiation available in the relevant band cap, and so you see more or less all the photons are used for this process, and also here the concentration of solar radiation helped to get higher yields and to have higher hydrogen production. To somewhat higher temperature and higher concentration. This is a reactor we used for thermochemical water splitting with ceria oxide. On the right hand side you see the reactor. The yellowish component is the so-called absorber, which absorbs the radiation which enters the reactor through a quartz window and is heated up to a temperature level of around 1500 degrees C. We apply a vacuum in order to suck off the oxygen which is set free from the ceria due to an endothermal reaction process. Here you see the principle. Concentrated radiation is heating the structure, and a little bit of argon is used to flush off the oxygen which is pumped out through the rear part of the reactor. If when the reaction is completed, then we switch the reactor to another mode, which is the oxidation mode. The temperature is reduced for that. We don't need solar radiation for that, and this is done at atmospheric pressure at around 900 degrees C. And for that purpose, we introduce water and CO2 as the feedstock. They are split. They are reduced into syngas, and syngas is the product which goes then into downstream units like a Fischer-Tropsch unit. Finally, I would like to show you one example of a demonstration of a full solar fuel production chain which was demonstrated in the course of a European project. It's a thermal process, so you have a solar tower arrangement. It was a setup which we did in Spain. Here the example, this is the size of the field including a tower. We have a control room in order to have a look at all the components of the process. The heliostat fields was able to provide a concentrated solar radiative power of up to 300 kilowatts, which was then used in 2 reactors on top of a small solar tower. It's only 15 meters high, so it's an experimental tower only. And there we had 2 reactors which were provided by ETH Zurich, developing them. Volumetric receiver reactor with the working principle I showed in a previous slide. And one of the reactors actually was used for the reaction, where the other was replaced by a calorimeter in order to get information on the energy balance of the process. And in addition, we also had a moving bar system in order to measure the energy density and the energy density distribution on the aperture of the reaction. And finally, we had, let's say, a small Fischer-Tropsch unit provided by the partner Hygear, a small company from the Netherlands, which was connected then to the product of our solar reactor. Here you get some impressions how it looked like in practice. On the top left, you see a bird's view on the facility next to the center of IMDEA Energia, and a partner of the consortium, and having their campus in the southeast of Madrid in Móstoles. You see a rather tight arrangement of the heliostats on the top right, which is due to the fact that we really needed very high concentration, and therefore you need a compact field capable to provide up to 5,000-fold concentration of the solar radiation. Yeah, here you see a little bit of a busy graph on the top left, showing different parameters. On the right-hand side, you see in red the temperature. It's going up between 1500 on the top level and 900 on the lower level, which shows the temperature swing operation, which you have in order to fulfill the requirements on the reduction step, which is high temperature, and the oxidation step, the hydrogen and CO producing step, which requires lower temperatures. We also have a certain pressure swing, which is needed in order to remove the products. And on the left-hand side, you see the flow rate of the components. You see either oxygen is produced or syngas is produced, and the rate between CO and H2 is only, let's say, determined by the ratio of the feedstock. On the right-hand side, you see the Fischer-Tropsch unit and also the product. We had a liquid fraction, which was close to kerosene, but further cleaning and separation is needed, but we also have a certain wax fraction. So in the end, we had to realize that further optimization of the Fischer-Tropsch unit and the catalyst is needed in order to get more liquid fraction. Yeah, with this, I'm already there. I'm already at the summary. I think I already mentioned most of the points I've listed here, and to save time, I would then go to the acknowledgement, acknowledging the support of different European and national and regional funding organization, giving co-fund to the different projects I have mentioned here on my slide. And with this, I'm ready to thank you for your kind attention.